It's a great pleasure to be here, and thank you very much for resisting the clarion call of any receptions you might have been invited to, and instead coming here for this presentation, which I hope to make truly worthwhile for you. It's the story of the Waratah Seed satellite and its team. You can see some of the members of, you cannot see the members of the team, but you can see the consortium that makes up this team. It's not something that is one person, such as myself. It's a group of over 100 people, 6 institutions in the consortium. You can see them there at the bottom. So you've got CUAVA, the University of Sydney, AXA from the University of New South Wales, Macquarie Uni, University of Technology Sydney, Delta V Space Hub, or New Space Alliance here, Sabre Astronautics, and major funding coming from New South Wales Government, and SmartSat CRC. And you can see Waratah Seed both here. This is a one-to-one model of the spacecraft. It's got, in fact, some engineering model payloads inside it, something that you might be able to look at afterwards. But you can see the actual flight model. Whoops, sorry, my apologies. The actual flight model here in its cage, so to speak, in the with its sibling CUAVA 2. And so I want to tell you about how we got from here to there, as in space. So first of all, the name Waratah Seed, where does it come from? You can see here the mission patch created for us by Grace Brown, who's a Wurundjeri woman. And you can see Waratah Seed here. This is a Waratah. How many of you have actually seen this in the wild? A few. That's great. And how many actually of you here are from the Waratah Seed team? I was hoping that some of those would raise their hands or stand up. So we had a number of the team members here. Any issues are to do with me rather than them, of course. But it is great to have you here, including some of the major engineering people, Patrick Opel, Shirley Bai, and Jung Ho Un, who did much of the heavy engineering aspects for the spacecraft. So where does it come from? It comes, as you see here, from the Eora word, which means seen from afar and beautiful, and perfect for a spacecraft that's going to go up into space and look down. Waratahs, of course, are also the New South Wales state flower, but they also grow all across Australia. And this is going to be particularly relevant to the last bit of the presentation. And seed, well, it's what we want to help grow a vibrant space economy and space sector in Australia, and for that matter in New South Wales as well. So I chose the name, and I figured there's no way that Investment New South Wales could possibly reject a proposal that was called Waratah Seed, because it really is what they wanted to have. So let's go on. So really, this is a talk about from here to there, as I said. Is it the beautiful desert, you might say, of Australia? A growing satellite scene, but poor compared with many other areas of the world. And getting to where we are today, where Waratah Seed was a month ago awarded the SmallSat Mission of the Year against a really impressive group of competitors. You can see here that you've got a number of, I think, 5 NASA missions, an ESA one, a number of small companies, and then ourselves right at the bottom. But very proud, and you can see here Shirley Bai and Jung Ho Un, who are here with the actual trophy itself. It is quite appropriately a small satellite, a cube even for a CubeSat, but it is tiny. It's approximately 4 or 5 centimeters on a side, so you can almost not see it there. So we're obviously very proud of this, and it's perhaps part of the reason why it's appropriate for me to talk to you about this project. But I thought I'd let this video do much of that work at the start.
Falcon 9 is in service.
This is the actual flight, as you can imagine.
-10, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ignition. And liftoff Falcon 9, go Transporter 11.
New pulse pitching downrange.
MOD chamber growth model.
This is the view from Vandenberg looking down. So in a nutshell, that's many aspects of Waratah Seed. Thought it was a useful way for us to start. And now I'd like to go into a little bit more detail, starting with what Waratah Seed involves and why, going on to talk about the genesis, how we actually grew into what we are today. And then right at the end, in number 9, we'll talk about one path into the future that we hope to go on, hopefully with many of you as partners. Number 4 is the payload competition itself. Waratah Seed project involved a competition involving startups to try and select some winners and go up into space with us, as well as commercial payloads. Then talk about the payloads and the satellite itself, so a little bit of the engineering, some of the results from those payloads, current status, some of the lessons learned, and the wider implications. And then, as I mentioned, one future path, which is, we're calling it now Waratah.space. And the intention is to go beyond Waratah Seed and have a payload pipeline to orbit for heritage, development, operation, and training, with regular cadence, something that people can plan with and bring us to a sustainable future for space in Australia. And for that matter, linking out into the wider world. So, really, what is Waratah Seed meant to be? It's the pilot space qualification project of New South Wales Government Space Development Strategy, or Space Industry Development Strategy. So it's a rideshare satellite, which for me means we are putting payloads onto a satellite. We're doing a lot of the help of the engineering of those payloads, the integration, the testing, the launching, all of the regulatory aspects, operating it in space, and doing all of those aspects. It's a 6U CubeSat. Most of the bus is commercial off the shelf for COTS, and the software also is coming from us. And we're looking at clients from industry mostly, and a few from academia. And the real focus here was mostly startups. So what are our foci? We're trying to develop and deliver space heritage for companies and other clients so that they can sell their products, their ideas, their data, and to develop the space sector in Australia and elsewhere. And that latter involves, of course, training people. And there are many aspects to that. Some of them are attracting payload clients, arranging and delivering a payload competition, helping to develop space-qualified payloads. Turns out that many of the ones that we had, even though there was a working prototype when they were given to us, would not have worked in space, and we did a lot of work together with the teams to bring them up to the quality required to survive the trip into orbit. Then, of course, developing, integrating, and testing the satellite itself and the payloads, the regulatory and legal aspects, commissioning, and then providing the payload data and operating proof, so as to actually have that space heritage that people could then use to develop further the way that they want. So this is just a slide again, emphasizing that it is the New South Wales State Pilot Space Qualification Project. It's intended to be low-cost access to space for, yes, New South Wales, but also Australia as a whole. And it's a consortium, not just one particular group. I should at least tell you what a CubeSat is. This, of course, is a satellite that's built of cubes of 10 centimeter on a side. So this one here is 3 cubes down, 2 across, 1 deep. So a 6U CubeSat. Sorry, I went and too far. I don't know quite why that happened. Okay. This idea of CubeSats, of course, goes back approximately 26 years to two people in California. And one of the expectations is that it's relatively light, about less than about 1.3 kilograms per unit. So these are not very heavy spacecraft. So why do you actually do this? Well, the real idea here is to allow the scientists, the engineers, the business people to focus on what interests them. To disregard the satellite, the CubeSat, as a tool. And the real question here is the one that I posed there. Do you want to actually design and build and operate and so on, or design and build at least your own fridge, your own PC? How many of you in this room have actually built their own computer? So I've actually got a surprising number here, approximately 10 people, which is actually really impressive, but probably not surprising, considering that most of us are space geeks. So why do you do it? It's really to have standards. Standards for the design, commercial COTS or commercial off-the-shelf parts and systems. So again, you're buying things you could build for yourself if you wanted to, but you probably don't really want to. It's much quicker and more efficient to buy them where you can. And so that makes the spacecraft much easier to build. Sorry, that's my fault this time. Much easier to build. Got reduced time from development to launch, which all of us want, especially both in academia and also in business. You're going for standard deployments and a piggyback launch where there's multiple satellites usually on that launch, for instance, with a Falcon 9 from SpaceX. And another idea is that you probably don't need expensive facilities. You need a room that's clean rather than a clean room. So it doesn't have to be expensive. If you've got really important optical components, you might well want to have a clean room involved, but maybe not otherwise. So there are multiple reasons for going for CubeSats in particular. And as I said, Waratah Seed is a 6-unit CubeSat. We've got approximately 1.5 U of satellite systems, not necessarily arranged in such a beautiful way as this, and then 4.5 U of payloads. We intended to have 1.5 U of competition payloads, and then 3 U of commercial client payloads that would pay more for the privilege. So where does Waratah Seed really come from a personal point of view? How many of you saw the perhaps rather terrible 1995 Power Rangers movie? This is the one in which, so it's only a few of you, which is perhaps surprising, but it's an age thing, really. My children love this movie, so I watched it a lot. And it involved Sydney, which you can see here with, sorry, keep on doing that. You can see here, this is the Sydney Tower, the MLC building nearby. This was actually used by the baddie in the film to pick up and use as a club. But we, as in this group of 5 of us, met underneath that in 2014. You have Andrew Dempster here from AXA, Brian Lim from Dandelions now, and Pollen One, Jason Held from Sabre Astronautics. And then this was the group of 4 of us that worked together at the start. We then brought in Tim Parsons here at the bottom as our first CEO, talked about various things. And one of the things we wanted to do, even at those early days, was to actually do rideshare. Just after the first Australian decadal plan for space science had come out in 2011, one of its ideas was to have small satellites. And so we really wanted to fit in to the environment here that might lead us into funding and actually being able to develop a space sector as well for Australia. It's worthwhile noticing that the Space Agency for Australia was only created in 2017. Or at least the announcement of the would-be one was 2017. The actual date was closer to 2018. So we then went ahead, a number of us, and built the first CubeSats. We have here UNSW ECO, Inspire 2, which is the one from the University of Sydney, which I led, and SUSAT, or SUSAT, which is from South Australia. They're all in 2017, so pretty quick that we got into this business, and then those re-entered in 2018. You might say, well, everybody's making CubeSats. Well, these are actually quite special. Inspire 2 was only the first Australian CubeSat and the fourth Australian-built satellite to actually work in space. So quite a bit of history there, and keep on doing this. And UNSW Eco was the second and fifth. And here's just a slide showing where the three of them were around the world at a particular time in 2017, in December. So you can see SUSAT, Inspire 2, and UNSW Eco. We then went on. A number of us were successful in applying for an Australian Research Council training centre in late 2017, and that got awarded roughly $5 million. And this was CUAVA 1, our first 3-unit CubeSat, unfortunately dead in orbit. So useful mostly from the point of view of looking at space weather-determined changes on the orbit of the spacecraft, as well, of course, of developing heritage and capability of building satellites. And we come now to CUAVA 2 and Waratah Seed, both 6Us now, so getting a bit bigger, both deployed in 2024 via SpaceX. So it's been quite a while since I at least started in this game. It's 10 years. It's required resilience. It's required evolution. It's required funding, all of those being vital. This is, of course, common for many people, but it's worth pointing out that it takes time to build things, usually. So that's enough about the background. What about the phases of Waratah Seed? You can see here a number of those phases. First of all, a payload competition to try and bring startups in and identify some of our initial small, probably payloads. We then wanted to attract commercial clients. We then wanted to get those payloads, develop them, help them be developed, test them, then eventually integrate the spacecraft, test it, launch and commissioning, and then operation in space. And as you know, not all of those are strictly in sequence. Certainly the first two you expect to go together. And of course, once you're in the payload development stage, you might well be doing some initial spacecraft integration via a flat-sat phase, then an engineering model built, etc. So it's not all sequential here. But it involved many members of our community, approximately 100 people, and we also learnt the importance of trying to reach out to the media and do public outreach, which, before I come to that video, I'll just talk a little bit about the payload competition itself. It's something that Jason Held from Sabre Astronautics led, and rather than having a shark tank for the pitches, we wanted to have a kindler, gentler environment, so a goldfish tank was what Jason wanted to have, which I think is a good idea. And there were three phases, here really, or pitch deck, 5 slides, then some mentoring and feedback, then a public pitch event with some VCs or venture capitalist people as well, including a prototype, which is which is a necessary requirement. We weren't going to go with things that were entirely blue sky. We wanted something that was achievable and launchable within about 1.5 to 2 years. Then a written application, and then selection, of course, via a committee. So not necessarily something for the faint-hearted, number of phases, but relatively quick to do. But of course, the first one, the zero-thought-of phase, is actually to attract those qualifiable, rather than qualified, but qualifiable applicants. Because someone who might not have been quite qualified in the first or the second phase might become qualified by the third. And we had a number of them that were in that category. Okay, so let's keep going. So this is one of our PR movies, tending to try and attract people to come and submit a payload or to be a private client on Waratah Seed. You can see a lot of pretty standard NASA sort of footage here about rockets going into space. But the questions, you know, are you ready to fly? Do you want to come? Do you want to try and join us? It's what we were going for. And I think here it goes on to talk about the winning groups. So this is a half and half type movie here. So here are the groups that actually won out: Spiral Blue, extraterrestrial power. We're going to have dandelions as well. We'll talk about more what they involved later. Space, and then Europa power I missed. And I think we'll just keep going. Okay. So it was one of the things that most of us don't feel very comfortable with PR and media. We decided that it was something we actually had to do and try and do reasonably well if we were going to be successful. So here, for instance, are 5 payload competition teams. You can see quite a range of differences here. 2 biomaterials/mechanical payloads, that's dandelions and Space. 2 sets of solar cells here, and then edge computing. And then we added on to that our commercial client payloads, one from UTS and Mawson rovers, and Spiral Blue again, and funded by SmartSat, which is thermal control, otherwise called Matilda. The NSW instrument, which is GPS reflectometry, which is called Harry. Sorry, keep on doing that. There we go. And then 2 others that we added at the end, in part because I'm director, and if there's a gap, I can put things on that I want. So you might notice that both of those are from the University of Sydney. One is a debris and plasma detection system, and the other is our electropermanent magnetorquer from Deneb, which you might have seen in the exhibition. So let's go on and talk a little bit more about those. And so here we have what should be a movie that's going to play. So we have here Matilda, 3 of the people, including, and we have AXA and UNSW with Harry 3. This is GPS reflectometry. Europa power here with their perovskite solar cells. You can see a small version of them there. Spiral Blue with their edge computer. Extraterrestrial power with silicon solar cells. We'll talk about them a little bit more later on as well. And Space with materials intended to go into a robotic arm. Dandelions here, biomaterials. And then we'll have Eddie as well. So first Deneb with EMAG. So this is basically an ADCS system that uses 1% of the power. And then Spades, or Eddie, as we call it sometimes here as well. So those are the systems. I can talk more about them, of course, if you want, but I'm going to leave it at that for the moment and go on and talk about some of the results. So the first one is Matilda. So this is the thermal management software, and the basic idea is to use 3D printed metamaterial heat sinks here to transfer heat from one place to another. You can see some of the contorted solar 3D shapes here for the heat pipes from one place to another. They're also filled with a phase-changing material, a wax, so as to increase the energy transfer here. And here's some of the results. What we have here is temperature as a function of time, the standard control here, and then we have with the phase-changing material. You see a longer time to get up to a higher temperature, and then it stays warmer for a long time. So much better operating time, and really a very nice system here set up. But I will keep going here. What about AXA? This is about GPS. So here we actually have the first results for Andrew Dempster's GPS instruments showing just standard PNT navigation, position, navigation, and timing. For the spacecraft, the blue corresponds to G-predict here, and the yellow is the trajectory coming out of the GPS. You can see they join on beautifully, so really good navigation. And this is the first time out of more than 5 experiments that Andrew's put into space that he was actually given the data, or able to get the data, to do the fundamental science and engineering he wanted to do on it. GPS reflectometry, standard aspect, of course, is that at your receiver you might have the direct path signal, but you also might see a signal bounced off the ocean or the land. And that can tell you things like the wind speed, well, it gives you the waves on the ocean, for instance, and from the waves you can work out the winds over the ocean, which of course difficult to detect. This is the type of signature that we expected to see in a so-called delay Doppler map, nice parabola like this. And what we have here in our actual results, mostly is noise, but we have a signal here that we think is this portion here of the parabola. So more research needs to go into this, but this is looking promising, at least, as being an evidence of GPS reflectometry. What about Deneb space? They're looking at EMAG, so a electropermanent magnetaucher, and this is for attitude control and determination on the spacecraft. So here you have Ann Bettens, Shirley-Ann Bai, and Zihao Wang. This is what we have, nice and small. And I'm just going to flip from this. This is something like a quarter U payload to some results here. This is rather complicated perhaps, but here you have volume, torque divided by power, the power efficiency, or just really the power used, and here's torque for various competitors, and then EMAG itself. And what you want to have is high volume efficiency, high torque over power, high power efficiency, and high torque. And you can see in this case that EMAG is doing extremely well compared with its competitors. And it uses approximately 1% of the power and gets 10 times the rotational torque. So it's really a very nice system that we're in the process of trying to commercialize. So what about next generation solar cells, silicon ones in particular, with extraterrestrial power? Here we have Peter Toth, the principal here, and Gavin Conabier is not, unfortunately, in this picture, but Shirley-Ann Bai and Patrick Opel. So a standard sort of thing, we're going to have solar cells that are standard or control, and those that were treated by extraterrestrial power. Got a radiation sensor in the middle as well, various sets of these controls. And the idea basically, which is pretty standard perhaps, is to have affordable power in space. So you want your solar cells to be mass manufacturable, radiation tolerant, pretty thin, and to be cheap in comparison with standard cells. So here are some of the data for extraterrestrial power. We have here the, in this case, this is the voltage as a function of time. So you're going into darkness here, back out into the sunlight, darkness again, and the solar cell currents here. And what you're getting here is a non-zero potential here, and that corresponds to actually giving power to the spacecraft. One thing that this has led to is a contract with Skycraft to actually use their solar cells on a commercial payload. So really an important step here and verifiable demonstration of how important the space heritage is. What about Eora Power with Anita Ho-Bailey here and one of her colleagues? And we're looking at perovskite solar cells, so a different approach, which is attractive in many ways because perovskites are much, much cheaper to produce rather than highly refined silicon, for instance. There's also multiple ways to manufacture it, and she's working on making those versatile and scalable. It's radiation tolerant, and here are some of the results. So the important thing here, 2 different cells, different colors, multiple iterations here, or rather multiple experiments in time. And what you're seeing is there's no hysteresis. Some solar cells will come down here, and then when they go back up, they go up here and then join back up. You do not want to have hysteresis. You instead want to have a cell that has essentially the same performance as you go to low voltage as high voltage, and that's what we're seeing here. Nice and stable results. They're not changing much as we go from one day to the next, so that's important. So it really looks very attractive for further development. And she, in part because of this, recently received an Australia Economic Accelerator Innovate grant to commercialize them further. So where are we today? What's our current status? Well, in April, New South Wales Government declared mission success. We'd accomplished all of the milestones there. We had 8 of our 9 payloads operating and giving data, including the 2 main ones, the one unit ones, Matilda and Harry. We have all of the satellite subsystems commissioned and nominal, and that remaining payload, we tried multiple times, but we think there's a software glitch on it, on the firmware, and we can't get anything out of it. It draws power, but unfortunately has not given us a 9 out of 9 success rate. But all of the payload teams have space heritage, and some of them have actually worked demonstrably in space as well. They're all NASA TRL 8, and which is above actually what we expected to do. Spacecraft have now been in orbit 13 months. They've traveled 1.5 AU or so around the Earth, and they're alive and well. Some hiccups. Our ground station today is, in fact, the last month or so has been in trouble. It's a UHF, VHF ground station. Had a lot of rain and storms in Sydney, and this seems to have been a major problem for our ground station. And that means we haven't been able to use the ADCS properly and troubleshoot some little issues on that, and we haven't had S-band data downlinks for a while. But this is just a snapshot from July of some of the work here that we were doing. You can see the different payloads on the left here, the last run, notes here, what we're going to do next, and we're looking at data being provided, people being happy, etc. So standard sort of operating log that you might hope to have anyway for your spacecraft. So this is just showing that we've gone 1.5 AU. We've actually drifted down from our initial altitude of something like 520 kilometers. We're now at about 490 down there. We're looking at orbital lifetime for at least another 2 years, especially given that we're now going into the declining phase of solar max. So we're looking forward to more data, more heritage for our people, and new opportunities. I thought it might make sense to talk a little bit about the wider implications and some of the lessons learned here. And I thought I might answer one of the burning questions that some of you might have, which is, how much does it cost? And so here, Waratah Seed is actually very inexpensive. Cash cost is about 1.8 million Australian dollars, the launch being about 0.35 million of that, so really very little. That doesn't include my salary, I do admit, but on the other hand, that's not close to $1 million a year, unlike various vice-chancellors at the universities. We have a very good rate of return on investment, rate of return investments greater than 10, for both New South Wales Government and SmartSats investments. So that's just taking actually in this case, it's taking the uplift in value for our startups, for just 2 of our startups, divided by the input. And so we're looking at huge returns on investment for our people. And so, of course, this is a good reason for people to fund a future Waratah Seed as well. Timeline's kind of impressive for many of people. We're looking at the last contract being signed in 2021 in December. Last payload decided quite a bit later, though, in 2023 in April. That was when we finally became economically viable to proceed on to the launch. So, it's about 1.5 years there. But then once we decided that, going on to launch was 1.25 years. So once we decided things, very quick, really, to get into space. So really, it's quite realistic to look at a CubeSat mission like this, with payloads being selected from industry and other groups, being 1.5 years, and it could be less. An important point here is also that academia, industry, government collaborations like this one really can work. They can work when they're provided by academics, which is not necessarily what all industry people believe, and they can do very well. And this, we led to 6 startups getting into space for the first time, and 1 university, UTS, going into space for the first time as well. So really, quite a number of firsts here. We have 8 of 9 payloads operational. Various people told me I was absolutely mad to have 9 payloads at all. They said maybe 1 primary payload and maybe 2 others. But given my heritage, I was born in Scotland, and we like value. So I wanted to have a spacecraft that carried as much as it could, sensibly, and work in space. And I think it shows that you can be ambitious with CubeSats and get almost all of your payloads to work in space, even if they're coming from startups and universities and other groups. So what about some lessons learned? One is that community engagement and development is really important, and for that, you have to have transparent discussions. You've got to tell people things. You've got to communicate. You can't just be the fearless leader and stand in one place with perhaps one other person and tell everyone else what to do. You instead have to bring them along on the journey and tell them when things are going badly, and of course, tell them when things are going well. Systems engineering, it's important, but it's not the be-all and end-all. You must have a process, but for me at least, you need to be flexible. Might mean you let your timing slide a little bit if you can catch up. Maybe your PDR or your CDR, your preliminary design review, or your CDR, they might not be as rigorous as a NASA one would be. But this isn't necessarily a NASA project. You do need to have lots of support, engineering support, especially we found for hardware and software. We have excellent people bringing in our payloads, but it's difficult to get multiple systems to work together. And that's where you need the engineering support. And it's not just the hardware, it's also the software as well. Because often our clients are not quite as ready as they think they are. Probably true for all of us in most aspects of life, but I think it's true here. As a theorist, I wasn't big on testing at the start, but I have accepted this mantra of testing, testing, testing. It's absolutely vital. And one thing that's, I think, particularly vital is to do a remote coming alive test, where you put your spacecraft on a lawn somewhere in line of sight to your ground station, you let it come alive, boot, set up the beacon, start transmitting, communicate back and forth, just like it would in space, but now it's on the ground, and if something goes wrong, you can actually fix it, rather than then tearing your hair out once it's in space and not being able to do as much as you want. An important aspect is that it's also not all just engineering and science. It's also finance. It's the legal stuff. It's the regulatory stuff. Things that most of us don't want to think about, but are absolutely vital if you want to get a project to work in space. And my final one is rather perhaps Scottish as well, but space is hard. I think we've all heard that multiple times, but I think finding paying customers is even harder. It's very rewarding, though, when that process works. So that's where we are at the moment. Where do we want to go? I want to show you one path to the future, at least for us, and that is encapsulated in the motto, a payload pipeline to space for heritage, for development, commercial operation, and training. Part of that means if it's going to be a pipeline, you've got to have a regular cadence of launches and payload provision. That cadence, we're going to go for a year, means you're going to have resilience and flexibility. Requires planning, of course, but that's what you want to have. You want to be regular. You want to be a pipeline. This is cost-effective, or can be. You can get large ROIs, or returns on investment, greater than 10. We want to go pan-Australian. One criticism I think we felt is that all of our payloads really came from New South Wales. We want to go pan-Australian, but we also want to go to neighboring countries and internationally. So whether that's Korea, Japan, Taiwan, it's other places as well, Europe, for instance, the US. Basically, if we can get a commercial client or payload within reason, we'll accept it if it's up to scratch technically, and it comes from a country that's not prescribed and that we think is reliable. We want to build a national capability that's a critical enabler and a resilient path to space. So it's not just for us, it's for other people. It's something to actually build a capability for Australia and for the region. And it's a whole of sector development. It's not just industry, and by this I mean it's the science and engineering, it's the academics, it's also government as well. And then it's the public as well. You know, what are we actually going to do with our assets that are in space? So all of these things are important: TRL uplift, technology demonstration, actual operation in space for long periods of time to provide people data and services that they actually want and can derive commercial value from, or public good value from. So it might be commercial, it might be data, but also education and training and outreach. All of those things I think all of us think are important. It's a question of how you do them, whether you have one path to them or whether you have many. So I have a last video here, which is showing one part of this. So it's not just ivory tower, we'll help you get your payloads into orbit. We'll also do all the regulatory and other aspects. So the date here is slightly wrong. It should be late 2027. So really we're intending to be close to full service. We won't develop all aspects of your payload, but we'll help otherwise. And we want to help you get into space and do things that are important. So we're looking for anchor tenants, for sponsors, for payload providers, all of these things. I think I'm going to stop here, though. So, various aspects to it. What does it involve? Well, we're probably looking at going larger, so to 12U, gives us 9U of payloads, roughly. So we're going to upgrade the CUAVA and Waratah Seed bus that has space heritage. We want to have an annual cadence with a set of 3 launches or projects at the start, looking at late 2027 for the first one, roughly a 1.5-year period for each one of those. But we want to evolve the funding model. Basically, we want to get as much of our funding at the start as possible so that we can then be precise about exactly when we're commercially viable and when we can go. So we want to have, ideally, multi-mission tenants, taking, say, 1U each, whether that's universities, whether that's government labs, whether it's companies. We also want to have groups that might want only a payload for 1 or more. Probably expect that the clients will give skin in the game payments. It's very easy to say, oh, it's too hard when you get given something for free. But when you pay, let's say, $10,000 for it, even though $10,000 is not a lot of money for many people, $10,000 is probably, 100 good dinners out, maybe more dinners, depending on who you are. And you usually care about that. But if it's free, you might not. So that's why skin in the game payments are often important. And this is the timing that we want to go for, late 2027. And we're calling it Waratah.space at the moment so that we have some heritage or continuity from the name Waratah Seed, but also evolution away from the seed into just space and being something that's regular and doesn't have a end of life necessarily. So here are the conclusions. You've heard most of them already. This is a project, a rideshare project. It's been declared a success by New South Wales Government, which of course all of you will respect, but also selected as the 2025 SmallSat Mission of the Year against a very strong field, I would say. We've got 8 of 9 payloads operational and producing the data that clients want. We've been 13 months in orbit. We've gone 1.5 AU around the Earth, so an amusing number for many of us at least. We've extended operations to the end of this year at least, and we're hoping to get more money from Investment New South Wales in particular, and perhaps some of our clients to go longer into 2026 and beyond. And the rates of return are greater than 10, just including just 2 of our startups' uplifts in value. So it appears pretty unique globally. This is a model that I haven't seen elsewhere in the world. It could well be that there is such a group, but at the least we're looking at a very successful, perhaps one of the most successful globally rideshare projects, and CubeSats in particular. We think the model is really quite attractive. You get TRL uplift for people, you build community, you train people. It's very cost effective, at least if you do it in Australia. It involves academic, commercial, industry, government collaboration, but delivered by academia. And we have a next step, which is Waratah.space, which is 6U to 12U spacecraft. Annual cadence, set of 3, looking at late 2027 for the timing. And we want to be pan-Australian and international, be resilient, build the ecosystem, be a critical enabler, and help with TRL uplift and operation. So it's not just getting into space, but it's really operating things in space there for continued and extended value. We have a consortium at the moment which we're keen to develop and extend, bring new people in. Perhaps some of our existing ones might want to evolve and off rather than stay on, but I hope they'll stay on. And we're looking forward to linking up with new people and really being a success going forward. And I hope you've enjoyed this presentation. I think there's one more slide here, which is really just a thank you from a number of our team members here, gathered recently. And you can see again here the members of the consortium here as well. So a contact number as well. And I look forward perhaps to being able to have some questions from you. But I'll go back to this slide, I think, for those. So thank you very much. And I'm the one who's in charge of selecting what questions get asked. So my apologies if I don't ask one answer one quickly. So the first one is anonymous, which is which ground station did you use? So we have a UHF-VHF ground station at the University of Sydney on top of the electrical engineering building, and we also that's for UHF-VHF, but we use commercial bands rather than amateur bands there, and we also do S-band via Amazon ground station, and that one is in Dubbo in Australia. Okay, next question. In your view, what should the balance be between university activity between basic research and commercialization? Oh, that's rather a topical one, a difficult one. I think it's a horses for courses thing. As in, some people will be good at basic research, and even some in applied research. Some will be good at the commercialization. It's rare to have people who can do all of those, go from fundamental research through applied into actual commercialization, and probably even fewer for whom the commercialization works. So I think both are important. All basic research, applied research, and commercialization are all important. Personally, I put more of the balance towards the basic and applied research than the commercialization for the universities. So another question was, with 9 payloads, how did you make sure one payload didn't run late and slow everyone else down? So this is really a matter of discussion and communication, and of course providing support to people. Beyond that, of course, there can be cases, well, there was a case where we had to decline to keep one payload on the spacecraft. That payload yeah, just missed all of its milestones. We weren't able to help them with the engineering aspects because it was a very complicated FPGA system and so on. And we just had to say, no, sorry, you're going to miss the deadline. We cannot accept your payload after this time. And they then had to leave. They, of course, wanted to say that they'd left, but of their own volition. But it's human nature. But I think that's the real thing is offer support, help as much as you can, but you can't then neglect the other members of the payload group, and you've got to be transparent about it and give them deadlines and live up to them. Okay, so next question is, how did you manage your radio frequency regulation approvals? So we'd done it before. So we'd done it before in the amateur bands. So we were quite confident in many ways. But then the amateurs, the IARU declined our request to use amateur frequencies. The Australian subcommittee of that actually approved our request. It was the international group that declined. We were, of course, really pleased about that. But we went to the commercial bands, and that required a lot of work by, in particular, Patrick, to go ahead and read up the regulations. And instead of employing a radio frequency engineer/expert to do the regulatory aspect, and we were told word of mouth that $100,000 was a not unreasonable number, which, being of Scottish extraction, I wasn't happy about. We talked with Patrick, and Patrick went ahead and did all of the analyses himself, and then we submitted to the ACMA, the Australian Communications and Media Authority, and they then, to and fro a little bit, but they accepted it. So we managed it. I think now the second time it would be very easy because we were quite clever in some sense with CUAVA 2 and Waratah Seed. We chose the frequencies to be exactly the same for them, even though they are in space at the same time, so that we didn't have any new people complaining about the frequency allocations. I think if I did it next time, we'd move it subtly one bandwidth away or two bandwidths away. Because usually you're advised by the ACMA to make your bandwidth requests relatively broad and then be flexible with it. So we just worked with the ACMA. We found them really wonderful to work with. Which I'm not going to answer the question about which payload was not successful, but the data is obviously in the presentation, actually, but I'm not going to go into that. Can you share about the regulatory challenges faced along the way? So we had to get an overseas payload permit for both spacecraft. That's an application to the Australian Space Agency. And we found them really helpful. We'd done this before, and the first time we did it, I drafted the application. It includes all sorts of things like simple things. What's the purpose of the spacecraft? Who are you going to have launch it? Where from? What's their track record like? Why should this be registered in Australia? As in, what benefit will it bring to you, etc. Who are the people involved in the team, including who's the person with whom the buck stops, so the highest officer. And they required, in my case, the email addresses, which is probably okay, and the private telephone numbers of the Vice-Chancellor and the Chancellor of the University of Sydney. I am not allowed to know that information, but that information has gone to the Space Agency. So yeah, what happened was in this case, the lawyer wasn't able to help us, so I drafted it, and then I sent it in. We revised a few little bits of it and went back and forth. And we found the process really very easy, really, and flexible. People were really good with us. So I actually think the regulatory people at the agency deserve, well, plaudits, at least from the Waratah Seed and CUAVA teams. We were really pleased with them. Ooh, a question. What was the most surprising hardware or software challenge? Gosh, I don't know. There've been a few. Oh, well, okay, here's one. One of the hardware challenges we suffered was with the ADCS for Waratah Seed. Because we were doing 2 spacecraft at the same time, which, by the way, I'd encourage people to make sure they do one first and then the other if they possibly can in the future. But we were doing 2 at the same time. And so we didn't have enough time to do the full ADCS testing for Waratah Seed. We did it for CUAVA 2, and we said, well, it's the same ADCS from a certain company, an international company, and so it'll be fine. We then found that CUAVA 2 was fine. We managed to commission the ADCS very quickly, point it where we wanted, etc. It was really wonderful. But Waratah Seed just would not go into, well, it wouldn't despin the way we expected it to. We found that it wouldn't point, it wouldn't go into White-Thompson mode as well, the way we expected it to. And so Shirley-Ann and Patrick and Jung-Ho were tearing their hair out, I think, for quite a while. And then we found out eventually that there was one subtle difference between the two ADCSs. One was the alleged upgrade of the other, and they didn't just upgrade the ADCS, they also flipped the coordinate system for the magnetometer without telling anyone. So all of the directions were round the wrong way. Once we fixed that, it was perfect. But that's probably the hardest, most annoying hardware challenge we had. I don't know that I can think of one for the software right at the moment. That's the sort of question to ask Patrick, probably, who's not right there at the moment. Maybe he's fled in the fear that you will have a lot of questions for him. So a last question here is, what are the key selection criteria for prospective startup partners? Well, that obviously depends upon the project. So for us, what we required was that it was the right sort of volume. So it was less than 1 U. The power restriction, power usages were not too big. The data volumes weren't huge. So that was one criterion. We wanted to have a prototype actually there in existence, so it wasn't just a blue sky idea. We wanted to have real benefit, in their opinion at least, as to why this should fly. So we didn't want to, I don't know, fly a box with a cockroach in it or something similar. We wanted something with real value. And we also wanted to have some certainty that we would be paid as well. So those would probably be the standard criteria that we had. If I added another one, it would probably be that they have a sufficient team. So it wasn't just one person, but a number. What would the number be? It's probably 3 or 4 people involved, different degrees, different technical strengths. I guess another criterion is that they have sufficient technical capability, well, to at least do the prototype, if nothing else. So that would be my answer. Does there happen to be anyone who wants to stand up and communicate a question otherwise? Okay. Okay. If not, then thank you very much.